This video is going to focus on tangent planes for multivariable functions. But for a moment we want to step back to Calc 1 and remember, okay, well, if we were given a function and a point, how did we find the equation of a tangent line at tangent line to the function at that point, right? And so I just want you to pause the video, and if you need to look up sources or kind of do a little bit of thinking, try to remember how we found a tangent line in this scenario. Okay, well, hopefully you had a chance to look, or you just waited and resumed the video. But remember, if we call this f of x is equal to y, we said previously in Calc 1 that, well, we could say we would find the tangent line. Okay, we said y tangent is equal to, we would have our point, and then we would add to it f prime at our point times x minus x0. And this, so again, this is the derivative, and we have our initial point. And again, you maybe just use point slope, so it would have just been y tangent minus y naught is equal to the derivative at x minus x0. And this, and again, just to recap why here, or why this formula popped up, well, certainly we have a point, we need to include that. And then why is it f prime? Well, that's because if you're looking at your function, and I'll just do a little quick sketch here, and okay, we have a function. I'm just going to do a basic parabola, and that's a very bad parabola, something like this. Okay, and we want to find the tangent line at that point. We had to know kind of the instantaneous rate of change of the function at that point. And again, okay, that's a bad example, or that's a bad drawing as well, but you kind of get the idea. Is at that point we need to know how it's changing instantaneously, and then we're making sure that it extends in that direction, and that's where the derivative came into play. But now we're focusing on multivariable functions, right? So we don't have just functions of x and y, we have x, y, and z, okay? And our goal is to find the equation of a tangent plane, and, well, you could do a line, but we're going to talk about planes if we're given a function and a point. Okay, so just a reminder before we get too deep in the weeds here, when we're talking about planes, there's different forms of a plane, right? There's normal form, which we might be, this might be the one that's the most rusty, but we would take a normal vector and then dot it with our x vector minus our point, x0, and technically I guess we can think of that as a point is equal to 0, okay? And so generally this has the form of something like a, b, c, and then we dot this with, let's see, x minus x0, y minus y0, and then z minus z0. Okay, is equal to 0. Okay, but then after a bit of math, we do some rearranging, and we say that this is really z is equal to, I call this standard form, z is equal to z naught plus a star, and I'll explain this in a minute, x minus x0 plus b minus, plus b star, and then y minus y0. Okay, and the b star and the a star and b star just come from, well, it's really going to be like a and b divided by c, because again you have to distribute, and okay, algebra. So that's kind of what I think of as standard form. And then there's parametric form, which, okay, rightfully has two parameters, s and t, as we saw previously, where we say that we begin with a point, so we begin with x0, y0, z0, something that is on the plane, and then we extend from the plane in two directions, s times vector 1, so I'm just going to call this, let's call it x1, y1, z1. Okay, so that's kind of our x vector, x1 vector, and then we add to this the other vector, so this is going to be kind of x2 vector, and I'm just going to call this x2, y2, z2. Okay, and these vectors have to be, or these parameters have to be in the real numbers. This video is not going to focus on the parametric form, but rather the first two. Okay, so we've seen these two forms. Which one do we want to use? Well, I'm going to say we're going to focus on the standard form in this video. We will give a brief wave to the normal form. In the next videos, you're going to discuss the parametric form. Okay, so to begin, there's an example here. Z is equal to x squared plus y squared, and I want you to name that surface. Okay, like really name it. Okay, hopefully you have a name in mind, and then we're given a point, and our goal is to find the tangent plane to z at P. And I'm going to hop into GeoGebra, and I have this created, so yes, it is a paraboloid. And so you can kind of see here what it looks like, paraboloid, and then our point A is also shown on there in a blue dot. You can kind of see the name, but that's what it's going to look like. Okay. And actually, you probably can't see the whole thing, so let's make sure you can. Okay, let me minimize this just a smidge. There we go. Okay, so now you can see the whole thing. It's a paraboloid where A is shown there. Alright, so now if we hop back in and continue our discussion, our goal is to find the tangent plane to Z at P. Okay? And so what we need to do is, okay, if we're using standard form, right, we can start here and say that our tangent plane is going to be, okay, just following standard form, so Z is 5, and then we have plus this A star, don't know what that is yet, X minus, and then 2 plus, and then 1, oops, nope, B star times Y minus 1. Okay, well that's a great start. I just need to find out what A and B are. Okay, and well, what are A and B? This is where, if we remember our Calc 1 ideas, we would, take a derivative and we'd evaluate the derivative at our point of interest, right? Well, now we have a multivariable function, so what is the equivalent of a multivariable derivative? And the answer is there isn't one. Well, okay, there is something called a total derivative, but we don't discuss that. What we actually end up using is something called a partial derivative. Okay, and what this is going to be is that if we have the function z, and z is equal to f of xy, we can say, and there's two different notations, if we do f sub x, that really means we're looking at the z function, and we're doing a partial derivative. Now we use kind of this thing that looks like a kind of a musical note of sorts. I think it does, at least. dz dx. And this just, we use this curly d to indicate that we're doing a partial derivative because we're only looking at differentiating one variable at a time. So this this derivative means we differentiate, okay, I'm abbreviating, differentiate z with respect to x holding y constant. Okay, so we differentiate as normal, except whenever we encounter a y, that is treated as a constant. Okay, so if we had just derivative of y, that would differentiate to 0 because it's constant. Similarly, f sub y is equal to del z, or dz dy. Okay, and so again, this is all the same, except you differentiate with respect to y, holding x constant. Okay, and all those mean copy above. Okay, so and so here we can't differentiate z with respect to z because that's weird. Okay, but in any case, now the next question is, do we need both of these for the tangent plane? And while I ask the question, you're probably like, yeah, you probably do. The idea here is that previously in Calc 1 we only had f prime of x, right? Because we were extending in one direction. Now, if we're looking at a plane, we need to extend in two directions and make sure that we continue in both directions from that point, okay? And just continue in a linear fashion. So yes, we do need. So really the form of a tangent line can be expressed as z naught plus, we are going to add to this f sub x evaluated at our point, and I'm gonna be lazy and I'm gonna write p, so we evaluate it at the point, okay, and then x minus x naught plus f sub y evaluated at point p, whatever that is. Again, I'm being lazy. Y minus y naught. Okay, so that's the idea that we are going to hang on to as we go back to our example. Okay, so if we do this, we can calculate f sub x as well. If we take the derivative of the function, right, holding y constant, this whole thing would drop off, and I would just have to differentiate x squared, so I get 2x. Okay. Similarly, f sub y is equal to 2y. Okay. So then at p, okay, what these become is just 2 times 2, so 4, and 2 times 1 is 2. Okay. So then our tangent plane equation here, so z tangent, is equal to our point, our z value 5 plus 4 parentheses x minus 2 plus 2 parentheses y minus 1. Okay, and just to confirm that this is indeed correct, let's look at GeoGebra here for a moment. And so pulling it up, I did put it in earlier, and yep, GeoGebra, so it looks like it actually cuts through the surface. It doesn't. It's just the graphics. If you kind of look edge on, it's perfectly straight. But otherwise, that does satisfy our conditions. Okay. One final comment here is that we use the standard form, but what does the normal form look like, right? So if we think about the normal form, well, if we have these two vectors that span the plane, and really these derivative vectors are, or these derivatives can be thought of as vectors, because again, you're extending in each direction. If we think of those two vectors as spanning the tangent plane, we can create the normal vector just by crossing them. But then the only question becomes, is it f sub x cross f sub y, or is it f sub y cross f sub x? Okay, and in each of the scenarios, you're likely going to have to play around a little bit. According to the diagram that I've drawn, I would need to, let's see, and again, according to the right-hand rule, we would take f sub y cross f sub x, but again, you might need to think of the vectors and sketch them to figure out if it is this, because ultimately what we want is we want an outward pointing normal vector. That's typically defined as a positive normal vector, and then if it's inward, it's negative. So if you happen to miscalculate, just slap a negative on it and you'll be fine. Okay, but this video has done kind of the job of introducing the tangent plane using kind of the standard form and, well, normal form at the end. In later videos, so next video you're going to talk about coordinate curves and use the ideas there, and then use those ideas as we look at the parametric form of the tangent plane in the final video. Okay, so stay tuned for those and enjoy.